Welcome back to the second part of Lagrange multipliers. We're just here to work out two more problems. So this first one, number 3, again, we're going to be using Lagrange multipliers to find our extrema. And we have f of x, y, z is x to the fourth plus y to the fourth plus z to the fourth. And then we have x squared plus y squared plus z squared is equal to 1. The second equation is equal to a number, so that means that it is our constraint function. So g of x, y, and z is equal to x squared plus y squared plus z squared equals 1. And then we're here to optimize f of x, y, z. So this is one of those cases where we have 3 variables, which means we'll have more equations to work with in our system. Fortunately, the gradients for these are not difficult. So first we're going to calculate the gradient of f is equal to lambda times the gradient of g. So I go ahead and set that up. The gradient of f, it's going to be the vector with all my first partials. Partial with respect to x is 4x cubed. Partial with respect to y is 4y cubed. And the partial with respect to z is 4z cubed. This is equal to lambda times, and then in my constraint, the partial with respect to x is 2x, with respect to y is 2y, and with respect to z is 2z. I love these problems where we have this kind of symmetry because it simplifies the derivatives, and it also, well, you'll see when we find the critical points, the symmetry leads to both good things and bad things. We'll see. So then the second thing we need to do is to set up our system using the gradient and the constraint, and then find the critical points. So from the gradient, we get 3 equations. We get 4x cubed is equal to 2x x lambda. In 2, we have 4y cubed is equal to 2y lambda. In 3, we have 4z cubed is equal to 2z lambda. And finally, in 4, we have x squared plus y squared plus z squared is equal to 1, and that's from our constraint. Okay, if we were to look at the first one, it looks like one of those equations where I could move everything to one side and factor and get a few cases. So I'm going to look at that. If I rewrite this, I have 4x cubed minus 2x lambda is equal to 0. There's a 2x in common. I factor out the 2x, leave behind 2x squared minus lambda. That's equal to 0. I get 2 cases. X is 0 or x squared is equal to 1/2 lambda. I'm not going to solve for the plus or minus here because I'm thinking about equation 4 where I have x squareds in there. Okay, now another case that I have, so this was from equation 1, I'm looking at equation 2, and it looks like that one's going to be very similar because we have 4y cubed minus 2y lambda is equal to 0. We pull out a 2y. It leaves us a 2y squared minus lambda is 0. So we get y equals 0, or y squared is equal to 1/2 lambda. Similarly, the third equation is 4z cubed minus 2z lambda. Pull out a 2z, leave behind a 2z squared minus lambda. It's equal to 0, and we get 2 cases. Z is 0, or z squared is 1/2 lambda. Okay, at this point it might be confusing. It's like, what do I do with this? I have all these things here. So we have a few things to consider. And maybe we should write these out. We have 4 cases to consider. And what they are is all variables 0, two variables, are 0. One variable is 0. And no variables are 0. Because all three of the variables have this possibility of either being 0 or non-zero. So we have to consider the case where they're all 0, 2 of them are 0, any two combinations 0, and then one of them is 0, any of those that could happen. And then, of course, none of them 0, which is the option where they're all equal to, or they all have a square that's equal to 1/2 lambda. So let's get started on those cases. Case 1 is the simplest case. In case 1, let's see, we're going to write this as x equals y equals z equals 0. So in this case, we have, if we substitute this into the fourth equation, we get 0 squared plus 0 squared plus 0 squared equals 1. It's not possible, so this is not satisfied. So we get no critical points from this case. Okay. Even though we got no critical points, it doesn't mean we don't consider it and write it down. So as you're doing your work, you still need to write down and show all your cases. You've got to be prepared to, explain this on an exam, like consider everything, okay? The next case, case 2, is where we're going to look at a few different cases where two variables are 0. Okay, so let's first consider where, let's say, x and y are 0, and z squared is 1/2 lambda. So I'm going to substitute these into equation 4. I get 0 squared plus 0 squared plus 1/2 lambda is equal to 1, which means lambda is equal to 2. And that further means that z squared is equal to 1/2 times 2, which is 1. And that means z is equal to plus or minus 1. So I'm getting two critical points from this. I get the case where x and y are 0 and z is plus or minus 1. Let me write that better. So the critical points are 0, 0, and then plus or minus 1. Okay. Let's see, if we were to substitute this into our function, f of 0, 0, plus or minus 1. Remember, f is x to the fourth plus y to the fourth plus z to the fourth. So we would be putting in plus or minus y and raising, or 1, and raising those to a fourth power, which gives us 1 in each case. So we just get a function value of 1. Okay, an alternate case here is where x equals z equals 0 and y squared is equal to 1/2 lambda. Well, in this case, we have 0 squared plus 1/2 lambda plus 0 squared is equal to 1. And again, lambda is equal to 2. But now y squared is equal to 1/2 times 2, which is 1. So y is equal to plus or minus 1. So the critical points here are 0, comma, plus or minus 1, and 0. This gives us the exact same function values. F of 0 with plus or minus 1 plus 0, and 0, that's going to give us just a plus or minus 1 raised to the fourth power, which is 1. Okay, third case under case 2 is where y equals z equals 0, and x squared is equal to 1/2 lambda. Again, we plug these into equation 3. We get 1/2 lambda plus 0 equals 1. Lambda is 2. X squared is 1/2 times 2, which is 1. X is plus or minus 1. Critical points, similar, plus or minus 1 and 0, 0. And then the function value, again, is the same. Okay, so that was 6 critical points that we got from the second case. All right, so we might have gotten none in the first case, but the second case gave us a whole lot. Okay, the next case, case 3, is where one variable is 0. And let's just block this off over here. Okay, if one of the variables is 0, let's just look at the case where x is 0 and y equals, sorry, not y, y squared equals z squared is equal to 1/2 lambda. Okay, so that means in equation 4 we'll have 0 squared plus 1/2 lambda plus 1/2 lambda is equal to 1. This means that lambda is equal to 1. And that means that y squared is equal to z squared is equal to 1/2. So y is equal to z is equal to plus or minus 1 over the square root of 2. Now, we're looking at all combinations of pluses and minuses in there because of all those squares. And so the critical points from here are 0, plus or minus 1 over square root 2 and plus or minus 1 over square root 2. Okay. Now, when I plug these into the function, I'm looking at f of 0 with plus or minus 1 over root 2, plus or minus 1 over root 2. Remember, these are all getting raised to the 4th power. If you take 1 over the square root of 2 and you square it, you get 1/2. If you square that again, you get 1/4. So we're going to get 0 plus a fourth is 1/2. Okay, the next case is very similar. It's the case where y is equal to 0. So if y equals 0, x squared equals z squared equals 1/2 y, or lambda. And similarly, I'm going to cut to the chase here. We're going to get x equals z equals plus or minus 1 over the square root of 2. So we get critical points of, let's see, plus or minus 1 over square root 2, 0, and plus or minus 1 over square root 2. And then we're going to get function values for these that are going to be the same as before. Okay. Lastly, we have if z is equal to 0, then y squared is, or sorry, I should say, start with x squared equals y squared equals 1/2 lambda. And again, similarly, we're going to get x is y is plus or minus 1 over square root 2. So the critical points will just have z equal to 0, and both x and y are plus or minus 1 over square root 2. And then that 1/2 is also going to be equal to our function value when we evaluate with these numbers. Sorry to gloss over that, but they really are the exact same thing. And so this happens sometimes when we've got these problems where we've got the sum of squares or sum of 4th powers. We end up with so many critical points. Like right here, oh my goodness, each of those is every combination of the pluses and the minuses. So that's 1, 2, 3, 4, 8, 12 critical points we just got on top of the 2, 4, 6 above. So we have 18 critical points right now. But they all gave us 1/2 for a value. And up above, we got 1s. Okay, so those are our values right now. But we're not done with our cases. That was just case 3. We need case 4. It's our very last one. So case 4 is actually pretty quick. We have x squared equals y squared equals z squared equals 1/2 lambda. So we're just going to plug those all into equation 4. We have 1/2 lambda plus 1/2 lambda plus 1/2 lambda equals 1. This is 3/2 lambda is 1. So lambda equals 2/3, which means x squared equals y squared equals z squared is equal to 1/2 times 2/3, which is 1/3. That means x equals y equals z, which is plus or minus 1 over the square root of 3. Okay, that gives us a whole lot more critical points, but we'll just write them very succinctly. As the critical points are all combinations of plus or minus 1 over square root 3 for all of these. Okay, and if we were to substitute this into our function, f of plus or minus 1 over root 3 for all three variables, we're going to take a 1 over root 3 and raise it to, let's say squaring would give us 1/3, squaring again would give us 1/9. So we have 1/9 plus 1/9 plus 1/9, that's 3/9, which simplifies to 1/3. Okay, so we have values of 1, 1/2, and 1/3. And so we want, it looks like the biggest one is 1. So we're going to say our absolute max is f of 0, 0 with plus or minus 1 equals f of 0 plus or minus 1, 0 equals f of plus or minus 1, 0, 0 equals 1. And the minimum, the absolute minimum, is the 1/3 value. So it's going to be f of plus or minus 1 over root 3 for all three variables. And that gives us 1/3. All that work to get two little lines of an answer. Okay. All right, next, how do we set up the following? So in the following, we're supposed to find extreme values of our function f, and it's on a strange region because there's an inequality, and we haven't worked with that before. So I'm really just wanting us to see how to handle it when you have a homework problem like this. In the past, our constraint is the one where it's equal to a number, but now we have less than or equal to a number. So the constraint is g of xy equals x squared plus y squared equals 16. But we also have an interior. And the interior is the x squared plus y squared is strictly less than 16. Okay, so when I'm thinking interior, I start thinking of what we did in 14.7 with the local extrema, where we would look inside of our domain and look at our first partial derivatives and set those equal to 0 and find if there are any extrema inside. Okay, so that's exactly what we're going to do. First, inside the domain of x squared plus y squared is less than 16. Solve f sub x equals 0 and f sub y equals 0 simultaneously. Okay, now f of xy is 2x squared plus 3y squared minus 4x minus 5. So I need to find f sub x of that. F sub x is 4x minus 4. Set it equal to 0 and solve to get x is 1. And f sub y is 6y minus, well, nothing. It's just 6y. So we'll set that equal to 0 and we get y is equal to 0. Okay, remember we want these two equations to be equal simultaneously, so the critical point that we get is the ordered pair 1, 0. Okay, and then I want to know what is our function value at 1, 0. Well, it's going to be 2 plus 0 minus 4 minus 5, which is -7. And I'll just highlight that. Because remember, we're going to go through and pick the largest and the smallest to be our absolute max and min. All right, next part, second, is to deal with the boundary. Okay, so second, let's just block this off. We're going to set up the gradient of f is equal to lambda times the gradient of g for the boundary, or for the border, where g of xy is equal to x squared plus y squared equals 16. Okay? So our gradient equation, or Lagrange multiplier equation, the first vector has our first partials with respect to x and y of f. So it's 4x minus 4, and then 6y. I'm just pulling what I got in the first part, equals lambda times, now the gradient of g is 2x and 2y. Okay, and then we want to get our equations from this. Okay, so we've got, maybe I should just move this. I'm all about organization and not making things be in weird places, but okay, here we go. So I'll get my equations. The first one is 4x minus 4 is 2x lambda. And the second one is 6y is equal to 2y lambda. And the third one is our constraint, x squared plus y squared is equal to 16. Okay, now I am noticing that equation 1 might not be the nicest one. Like, I can't factor anything out. If I move everything over to one side, I won't be able to factor and solve for anything. But equation 2, I can do that, so I'm going to do that. I get 6y minus 2y lambda is equal to 0. Factoring out a 2y leaves behind 3 minus lambda. Set that equal to 0. Y is 0, or lambda is 3. So this gives me case 1, and then case 2. All right, now I'm going to go up here and start examining case 1 and case 2. So case 1 is where y is 0. Okay, if y is 0, then in 3, I have x squared plus 0 squared equals 16. And so x is plus or minus 4. Now I didn't plug y equals 0 into equation 1 because there is no y in equation 1. So it doesn't really help me. But I can find 4 and negative 4 in equation 3. So now I get critical points of 4 with 0 and negative 4 with 0. And the function values, I need f of 4, 0 and f of negative 4, 0. F of 4, 0, let's see, we're plugging it in. We've got 2 times 16 plus 3 times 0 minus 4 times 4 minus 5. And I've already done the math on that. That's going to add up to 11. And when I do negative 4, 0, I get 2 times 16 plus 3 times 0 minus 4 times minus 4, and then minus 5, and this will add up to 43. Okay, so I have 2 more values from critical points from case 1. Now case 2 is where lambda is equal to 3. Okay, if lambda is equal to 3, I can substitute this into equation 1. So I get 4x minus 4 is equal to 6x. I move stuff over, I get minus 4 is equal to 2x, or x is equal to negative 2. And then sub into 3, and we get x squared, so that'll be negative 2 squared, plus y squared is 16. So y squared is 12, and y is plus or minus 2 square root of 3. Okay, so I got 2 more critical points. We have negative 2 with positive 2 root 3. and we have negative 2 with negative 2 root 3, and we can find the function values of those. F of negative 2 with 2 root 3. I did the math on that one already as well, so I'm just going to give it to us. It's 47. And then f of negative 2 with negative 2 root 3 is going to work out to 47 as well. Okay, so you can see we've got a few things highlighted. We have a number of values from critical points. We have negative 7, which appears to be the smallest. And we have 11, we have 43, and we have 47. Okay, so it looks like the absolute min came from that interior point of f of 1, 0 equals negative 7, and the absolute max is coming from what we found here, which it looks like f of negative 2 with plus or minus 2 root 3 gave us 47. Okay, so the only difference in this one was really that we had to look in the interior. So this inequality that's up here makes you look at interior. So pay attention to that if you come across any in the homework. All right, one more problem. And in this one, we're working with one of these application problems, and we saw something similar to this with absolute extrema. And in absolute extrema, there was actually, in all of the application problems, there is actually a constraint, but the way we deal with it is different in 14.7 than it is here in 14.8 with Lagrange multipliers. So in this particular case, we're supposed to find the points on the sphere, x squared plus y squared plus z squared is 4, that are both closest and furthest away from the point 3, 1, negative 1. So we're looking for 2 points. One that gives us the farthest distance and one that gives us the closest distance, okay? Now, notice that like if we were just looking at the distance from the point that's given to any old place in space, then there would be no constraint because it's just any place in space. Our constraint is actually the figure that we're examining, the sphere. So this x squared plus y squared plus z squared equals 4. That's our constraint. So that's g of x, y, z is x squared plus y squared plus z squared equals 4. We have to come up with the function to optimize. So that function has to do with distance because that's what we're being told to find. So we should come up with a distance function. So the distance, well, let's start with this actually. Let's let x, y, z be any point on the sphere. Then we're going to find the distance between the x, y, z and the point that's given, the 3, 1, negative 1. The distance is d equals the square root of x minus 3 all squared plus y minus 1 all squared plus z minus a negative 1 or z plus 1 all squared. Okay, so then the distance is this guy, and this is what we optimize. But it is analogous or the same to optimize d squared. Okay, so we're going to look at the squaring function instead, because if we find that the closest point is some point, the closest point for the distance function is also the closest point for the square of that distance function. Okay, so that shouldn't change what we find. So I'm going to let f of x, y, z equal d squared, which will be the x minus 3 all squared plus the y minus 1 all squared plus z plus 1 all squared. Okay, that's what we're going to optimize. So first, set up the gradient of f equals lambda times the gradient of g. Okay? We just found our f, so let's go ahead and get the vector with all of the partials in it. First partial is 2 times x minus 3. With respect to y is 2 times y minus 1. With respect to z is 2 times z plus 1. Equals lambda times, now remember our constraint function is the actual sphere, and the first partials are 2x, 2y, and 2z. Okay. Set up the system with gradient and constraint. This gives us 4 equations. We have, and I'm going to go ahead and distribute as I write these out. So from the gradient of f, the first equation, I have 2x minus 6 is equal to 2x lambda. In 2, I have 2y minus 2 is equal to 2y lambda. In 3, I have 2z plus 2 is equal to 2z lambda. Okay. Now, this is a weird one, and this is one of the reasons I chose it, because it is really weird. I don't have any, oh, sorry, I forgot one equation, my constraint. X squared plus y squared plus z squared is equal to 4. Okay, I cannot actually move everything over to one side and solve and get a few cases in any of these. I can't really substitute any of these into each other either. However, what I could do is notice on the right-hand side of, for example, the first and the second. They're almost the same. They both have a 2 and a lambda, but one has an x, the other has a y. So if I was to multiply the first equation by a y and multiply the second equation by an x, then the right-hand sides would be the same. So I'm going to try that. Multiply the first equation by y, I get 2xy minus 6y is equal to 2xy lambda. The second equation, multiplying by x, I get 2xy minus 2x equals 2xy lambda. Okay, well, I have two equations, and they're equal to the same thing, which means that they should be equal to each other. That means 2xy minus 6y is equal to 2xy minus 2x. Now, if I move everything over to one side, what ends up happening is those 2xy's go away. So I'm just going to have minus 6y equals minus 2x. So I could solve for x. X is going to be 3y. Okay, now I have a relationship between x and y. I know that x is 3 times y. Now what I want to do is go in here and do the same sort of relationship with equations 2 and 3. Okay? So when I do that, I'm going to multiply equation 2 by a z, and I'm going to multiply equation 3 by a y. Okay, equation 2 multiplied by z becomes 2yz minus 2z equals 2yz lambda. Equation 3 multiplied by y becomes 2yz plus 2y equals 2yz lambda. Similar thing here. I have two equations. They are equal to the same thing, which means they should be equal to each other. So this means 2yz minus 2z is equal to 2yz plus 2y. Getting rid of the 2yz's, I'm left with minus 2z is equal to 2y, or z equals negative y. So now what I have here I have x in terms of y, I have z in terms of y, and then y is y. I could take all of these and sub into equation 4. Okay, again, I know this is not intuitive, and I don't mean to make it look like this should be easy. It is not. I could sit and stare at some of these for a while before I figure out what the first step is or how I should work through them, but I have worked through enough of them that it's gotten easier. Now I know that there are certain tricks that always come up, and so that's where you want to get to in your homework is you're working through these problems and you start to see similarities between problems, like, oh yeah, that technique I used in problem 7 will work on problem 13 or whatever it is. Okay, so we're going to substitute all of these into equation 4. X equals 3y, y equals y, and z equals minus y into 4. When we do that, we get 3y all squared plus y all squared plus negative y all squared is equal to 4. This gives me 9, 10, 11 y squared is 4, or y is equal to 4 over 11. Sorry, that's y squared. So y is equal to plus or minus 2 over the square root of 11. Okay, and let's see, if y equals positive 2 over the square root of 11, then x is 3 times that, so 6 over the square root of 11, and z is negative that, so z is negative 2 over the square root of 11. So the critical point there is 6 over square root 11, 2 over square root 11, and negative 2 over square root 11. And the function value at this point, we're going to plug this into our function and actually, wait a second. We have to be careful about this because when we plug it in, let's go back upstairs and see what the heck are we doing here. Let's see. We want to find the points on the sphere that are closest and furthest away. We found 2 points. We need to figure out which one's closest and which one's furthest away. So what we actually want to find is the distance, not the function f, because f, remember, is the square of the distance. All right. So I'm going to change that to d of, so this is going to be the distance between the point we were given and then this point is going to equal, and just trust me on this one, okay, it's actually approximately 1.31662479. That's what my calculator gave me. Now, if y equals negative 2 over square root 11, x will equal 3 times that, so negative 6 over square root 11, and z will be equal to negative that, so positive 2 over square root 11. The critical point is negative 6 over square root 11, 2 over square root 11, nope, sorry, negative 2, and then positive 2 over square root 11. And then the distance function evaluated at this point, I plugged it into my calculator because it's pretty ugly, but what it gives me is approximately 5.31662479. Okay. These are the 2 distances. Clearly one is bigger than the other. Okay, so this critical point up here is the closest because it is the shortest distance between the 2 points. And this second critical point down here, that is going to be the furthest away. Okay, so with these word problems, you always want to go back after you find your critical points, like go back up and remind yourself, what were they asking me? What was it that I was supposed to find? Did I find it? And how do I answer the question that's being posed? That's it for 14.8 Lagrange multipliers. If you do have any questions, please reach out.